If Davison and Germer had used 100 volt to accelerate their electron beam instead of 54 volt, what is the wavelength of the electron? Okay, this is about electron diffraction. Okay, he used this potential difference of voltage to accelerate the electron. This is in the accelerating chamber. Yeah? Accelerating chamber. Here it seems to have 2 voltage. Okay, it seems to have 2 voltage. We put as V1. No. The V1 supposed to be this one. This one should be the original. Okay, this one supposed to be the original voltage, V1. Now he used a new voltage instead of the original one. Yeah, the new voltage is 100 volt. 100 volt. So okay. So here seems to have 2 conditions. 2 conditions. So I better make it into column. Yeah, 2 column. So condition 1 and condition 2. Okay, and don't bother about below. Yeah, I will explain about it later. Okay, so here you can see there are 2 conditions. The original condition and this is the new conditions. And what is the changes in those values? Yeah. What is the wavelength of the electron? So he asked for the wavelength for the new conditions. Okay, so we can say this is the lambda 2. We need to find the lambda 2 when using 100 volt. Yeah, instead of 54 volt. What is the wavelength when using 100 volt? Okay, so seems that not much information given here. So he didn't give the wavelength for original conditions. So never mind, just write it down. So we have the original condition V1 and the new condition V2. Okay, so how to relate the voltage to wavelength? How to relate the voltage to wavelength? Still remember? Electron diffraction. This one. Maybe I just copy this one and go ahead to these questions. Yeah. See this one? Still remember about the electron diffraction? Yeah. So about the electron diffraction, see? How to relate the voltage to wavelength? How to relate the voltage to wavelength? So you see here electron diffraction. So in the accelerating chamber, you increase the voltage. You put a high voltage. You increase the velocity of electron. You accelerate the electron to a very high velocity, very high kinetic energy. So at very high velocity, at very high, like this one, at very high velocity, you will have a small wavelength. You have a small wavelength. So this is the 2 formula that describes the relationship between voltage and wavelength. This de Broglie wavelength formula. So just use these 2 equations. First, you substitute the voltage into here, the voltage V. Find the velocity, velocity of electron. Once you got the velocity of electron, you substitute into de Broglie equation, velocity here. The mass, just put mass of electron because we are using electron. Put the mass of electron, and then you can find the wavelength. You can find the wavelength. So these are the 2 formula. What is it? EV equal to half mv square and lambda equal to h over mv. This one lah. Yeah. EV equal to half mv square, lambda equal to h over mv. And we use mass of electron, okay, because we use electron beam. Just write it down here. This is the electron beam, so we use mass of electron. Okay, do you know what's the mass of electron? 9.11 exponent negative 31. Can find in the list of constant. And then the charge of electron, this one use charge of electron, 1.6 exponent negative 19. Now, is there a more direct way to find from voltage directly to the wavelength? A more direct way? Yes, these 2 formula, if combined, you get this formula, which I say about this one lah. Yeah, these 2 formula, EV equal to half mv square and lambda equal to h over mv. If these 2 formula combine, you get the new formula which relate the voltage directly to the wavelength. Do you see that? It relate the voltage directly to the wavelength. Instead of need to find the velocity of electron, no need to find the velocity anymore. You just put in the voltage here, you immediately can get the wavelength. This formula will be provided in the list of formula, yeah, in the exam. Okay, so you can make use of this formula also, a more direct formula. Okay, or if you forget about this formula, you can just go back to the concept. Go back to the concept, use the EV half mv squared and lambda equal to h over mv. Right now, I just use the direct formula, this one, yeah? These two formula combined, you get this. Okay, just now I talked about original condition and the new conditions. Now, do we still need the 54 volt? Do we still need the 54 volt? Or is this new condition information is already sufficient? You look at here, we to find the wavelength of electron for new condition, which is I put as lambda 2. This one should be lambda 2. This is the voltage 2. I put in the voltage 2. I put in the lambda 2. So, do we still need the original condition? The mass of electron, I can find the list of constant. The electron charge also I know in the list of constant. So these two values already given. The voltage is 100 volt. So is enough information to find the wavelength. So I no need to refer to the first condition anymore. Okay. At first I thought we need to do comparison. But then it seems that we have already enough information. So this 54 volt actually is just extra information. Extra information can be ignored. Yeah, can be ignored. So just use this one. Okay, so this one h is 6, also a constant value, 6.63 exponent negative 34. Okay, and then divided by this is quite a long one. 2 times the mass of electron is 9.11. Exponent negative 31, and then electron charge is 1.6 exponent negative 19 coulomb, and then the voltage is 100 volt. The voltage is 100 volt. So just put in the 100 volt there. 100 volt. Okay, now I can find the wavelength. Let's calculate. Yeah, let's calculate. Okay. So I got my answer is 1.23, 1.23, which is exponent negative 10, meter. Okay, so this means that the answer, what's the answer? It is in nanometer. Not necessarily have to change to nanometer. You just leave at SI unit is very good already. But if you want to change to nanometer, this is exponent negative 9. Okay, this is exponent negative 9. So I need to get exponent negative 9. That means this is negative 10. So I need to make it bigger, the value. So this one, negative 10. That means this one is 12.3. And this one become negative 9. This one become negative 9. Isn't it? Wait a second. Sorry, I'm wrong. I'm wrong. If you want to make it negative, that means I want to make it become this exponent negative 10. Actually, it means exponent negative 1 times exponent negative 9 meter, because I want the negative 9. You see that? Sorry. Again. So negative 10 is actually negative 1 plus negative 9, so it's negative 10. So this negative 1, exponent negative 1, multiply to the front. So what do we get? So if this one multiply exponent negative 1, so it becomes 0.123. 0.123, and then this negative 9 become nanometer, so which is 0.123 nanometer. That's the answer. Okay, Or you can just leave it at the SI unit. So is the answer correct? Let's check the answer. Yes, it is 0.123 nanometer, which I get the answer correct. 0.123 nanometer. Okay, so see you in the next video.